Hey, cut.
זה פשוט יעבוד מעצמו כאילו, מה אני גם בלי לא ברור למה צריך את זה, אבל אחרי מה עושים את זהו, רגע. נראה לי עדיף אנגלית, אף פעם לא דיברתי את זה בעברית. רק אברי הלך. אוקיי, אין לי מושג אם זה דולק או אם שומעים אותי
מישהו בזום רוצה להגיד אם שומעים.
יש בן אדם אחד, אז אני פשוט לא רואה את המספר.
שומעים, תודה. שומעים.
טוב, רגע, טוב, אז היום מדברת איתנו מור גבע, היא עשתה את הדוקטורט במפלגה של יונתן ברן, עכשיו ב-AI2 ועכשיו היא בגוגל, והיא תדבר איתנו על מיני מודלי שפה אינטרפרטביליים ורובסטיים.
אולי רובסטיים, לא בטוחה על זה, אבל כן. Okay, so hi everyone, thank you so much for coming. I know it's the end of the semester and probably you have a lot on your minds. Yeah, so I'll talk about reverse engineering language models for interpretability, control, and efficiency. Right, so large language models like ChatGPT and BARD, I'm sure everyone here heard about them. They have become an integral part of our everyday lives, right? We use them to write, to search, to code, to build new products, create ideas, whatnot. I'm hearing myself. Okay. Yes. So, or like the Forbes magazine said, a wave of billion-dollar language AI startups is coming. So what are these language models? Essentially, these are neural nets trained on large volumes of textual data for next word predictions. So we just take a lot of text from the internet, from books, we feed it as inputs to these models, and we optimize them to predict the next word for a given sequence. And this process results in amazing models that can understand and generate human-like text surprisingly well. So AI21 did an interesting experiment. They called it social Turing test, where they let users interact with these bots like ChatGPT for 2 minutes. And at the end of the session, they asked the users whether they interacted with the bot or with a fellow human. And these are the results. So a random guess, right, is 50% chance to succeed at this task. And in 40% of the cases, the users actually guessed that the bot that they were interacting with is a human, right? Just to demonstrate how good these models are. And you know, despite this like rapid progress in natural language processing, the sad truth is that we don't really understand how these models work, what they can and what they cannot do, right? So we use them everywhere without knowing how they work. And you know, beyond like curiosity, this has like real implications. So there are a lot of problems, just to name a few. recently it has been shown that these models tend to generate a lot of misinformation in a plausible way. Right? So as models become larger, right, and modern models are getting larger and larger, they also tend to generate more information that is basically incorrect. Here's another example. So models also tend to memorize a lot, right? So we train them on a lot of data. It could also include personal or proprietary data. And these models capture that, and we can also extract memorized information from them. So this also raises all kinds of security concerns. And beyond all these model behaviors, right, there's also a very high cost in just building and just running these models, right? So just to give a few examples, one of the recent models trained by Google, the estimated cost for training this model is over $20 million. And the monthly cost just to run, right, just to serve ChatGPT to end users is estimated to be $3 million. And it's not just money, right? There's also very high environmental costs. Just to run these models, it takes a lot of GPUs, TPUs. Yeah, so that's also a big issue. And yeah, I just gave a few examples, but there are many more actually. And maybe what I'm trying to say is, we build these models, we use them for everything, but it should come with some responsibility. We should be able to control these models to some extent, or at least understand what we are doing. Yeah, and so previous works actually tried to understand those, to answer those questions. So here are just maybe the three most common approaches applied in the field of natural language processing in the past few years. So maybe the first one is that identifying salient words in the input, right? So when we feed some input to the model, we try to identify the most influential parts in the query that influence the most on the output of the model. Another very common example is behavioral testing, right? So to understand if a model actually can do a specific task, we just build unit tests, right? We build test suites that we run the. By the way, feel free to interrupt with questions. Yeah, so we just run a lot of perturbation of the task to see if the model consistently succeed at a task or not. And finally, probing. So this is maybe the most popular interpretability approach for these models. We basically train classifiers on top of model representations to understand whether they capture a specific feature or not. But all these models, they kind of miss a key ingredient. They try to probe the model from outside while still thinking about it as a black box. What I'm trying to do with my research is to understand how models operate on their inside, how exactly these models, these large, deep neural networks, make their prediction, how they build it, why they make certain predictions. I draw a lot of inspiration from my past experience in the cybersecurity domain, actually, where I analyzed or reverse engineered malwares. So language models arguably can be viewed as compiled programs, right? Like we have binaries that we can run on all sorts of inputs. We also have language models that we run on textual inputs. And for compiled programs, we have a lot of tools to analyze what they're doing, to go back from binary to logic, right? So we have, for example, these assemblers where we take a binary file, convert it into assembly code, from which we can derive the logic of the program. But we do not have such tools for language models. Language models are used as black boxes. And this is what I'm trying to do for language models. So just to continue with this analogy, this task of understanding these neural networks is super hard. So this is a pyramid that describes the difficulty level of different analyses for malwares, right? So at the bottom of the pyramid, we have fully automated analysis. This is like antiviruses or scanners. So in the world of NLP, this is like benchmarks. We have hundreds of benchmarks in NLP to see how our model is doing. There are a lot of noise there, and I don't know, just before the talk, Yair here mentioned how many problems we have in that. So this is benchmarks. Then we have static properties analysis. This is basically understanding things about the model without actually using it or running it. Then we have interactive behavior analysis. This is what NLP researchers have been done until very recently. And then maybe the most hard analysis type is actually code reversing. And this is what I'm going to talk to you about today. So I had a bunch of works towards this goal, but today I will focus on 3 of them. And here's the plan for the rest of the talk. So I'll start with a quick introduction to transformers. Transformers are the neural architecture that underlies all models, modern NLP models today. It underlies ChatGPT, GPT, BARD, you name it. Then we will analyze one of the building blocks of these models, the MLP layers, to understand their operation and how they build predictions in transformers. Then we will demonstrate practical applications of these findings to show how we can control predictions from these models and also improve their efficiency, computation efficiency. And the last work I'm going to present will be about how these networks store and extract factual information that they capture during training. And then we will conclude with future directions. And like I said, please feel free to interrupt with questions. All right, so Transformers 101. What are these language models? So we feed them input, essentially text, right? We start from string, like the cat sat on B. Then before we do anything, we first break it into a sequence of tokens. Tokens are the basic units these models are trained on, right? You can think about tokens as words, for example. So for a given string, the cat sat on B, we'll just break it into 5 tokens. The cat sat on B, right? And then each token is first represented as an embedding vector, right? So essentially these models work on a continuous space. Words are discrete. They come from a fixed vocabulary. And so we first represent each token as an embedding. Then these vectors are being transformed across layers, neural layers, right, of 2 types. We have multi-head attention layers, or in short, just let's call them attention layers. These layers perform global updates. They take all the hidden representations, all these token representations in each layer, in the previous layer, and aggregate information across these representations. And the second type of neural layer is the multi-layer perceptron, or MLP in short, right? And these make local updates. They operate on each token representation alone, right? Great. So we have these token representations at each layer, and then to get a final prediction, to get the next word prediction, we simply take the last layer, hidden representations, token representations, or even just the last one, and then project it to the embedding matrix, the same one we used at the beginning, and take this a softmax to get a distribution, a probability distribution over the vocabulary. So let's say we want to get the next token prediction, we can either take an argmax or a sample from this distribution. Any questions on that? Right, so you know all about transformers. Okay, great. And so, yeah, like we said, we know exactly what the inputs are, right? These are strings that we can understand. We also understand the output. And the big question here is what's going on inside? Because some queries can be very complex, right? We can ask questions like, I don't know, did Aristo use a laptop or something like that, right? Which are not so easy to predict. And so this computation is very hard. And so this is what we want to understand. Great. So yes, in my research, I had 2 key observations about that. Here's the first one. That operation that we apply at the end, where we take that token representation and convert it into a distribution, technically, we can apply it at any layer, right? So this can give us a distribution, like to see the evolving distribution of the output distribution across layers. Now, obviously, these models are optimized just to give us that representation at the end. So why would it work? Well, empirically, it just works way better than we would have thought, and we will get to that a bit later.
So but more when you say work, what exactly do you do with the sequence of distributions?
So what I mean by work is that when I take that inner vector during the computation and project it, I get like a sensible distribution. I get distribution that makes sense. That the top scoring tokens are plausible continuations to the input, for example. I don't this is not obvious to happen, right? You could get
very strange because it means that even though one layer could be a rotate, if you take the space, just rotate it, do something that's one-to-one, it doesn't do it. Because then you
so the naive assumption here is that the naive assumption behind this is that all the layers operate in the same space. This is an approximation. It's not exactly the case, but yeah, like I said, it works very well, and there are a lot of improvements we can make to that approximation. Yeah, but it's surprising, and we will see how exactly we benefit from that.
But it doesn't make the process more deterministic if you make max all the time instead of a distribution, because distribution gives a lot of entropy and a lot of possibilities, while softmax make it more deterministic.
Oh, you're asking about the softmax?
Yes.
Oh, yeah, I mean, essentially, this is just what you apply at the end because you want to treat it as a distribution because you sample from it. I mean, this is what.
No, but if you do it all over the layers, then making the whole process more deterministic.
Oh, so just to clarify, this is inference time. I'm not training the model, right? I'm just using a fixed model. I do not change its operation really. I just try to inspect what's going on. Imagine that I come with a magnifier. I'm like, okay, how the distribution looks at this layer? How the distribution looks at this layer? Right?
Oh, okay.
Okay. Any more questions?
So you didn't tell us yet what you do.
Oh yeah. This is just like a general observation. Great. Okay, right. The second one is that we can view the token representation construction across layers as an information stream, where each layer in the network, whether it be the attention or the MLPs, they first read from that information stream, make some computation, and the result of that computation is being added, it's being written back to that information stream, right? So the interesting insight from these two observations is that, if we have a way to inspect the evolution of this output distribution, and each layer, the layers essentially build the output distribution, and each layer reads and writes from that, maybe we can interpret the operation of these layers in the same space, in the space of the vocabulary. Okay, great. So following that intuition, we turn to analyze the operation of the MLP layers, one of the building blocks of transformers. And before I dive into the details, maybe a good question to ask at this point is like, why the MLP layers? So transformers, okay, so first of all, maybe, these layers just account for most of the network parameters. So yeah, they have a lot of expressivity in them. And yeah, maybe the second point is the most important one. When transformers came out 6 years ago or so, it was all about attention. Maybe some of you are even surprised when I say, where does a meet? Yeah, so when transformers came out, the title of the paper was, attention is all you need. Well, that's not true. If you train transformers without the MLP layers, you won't get any of the same performance. So yeah, a lot of analysis was done on the attention layers, but nothing almost on the MLP layers. Yeah, and in the first work, I'm going to present the follow-up one, but the first work in that direction, we showed that these layers actually can be viewed as key value memories. So they store a lot of knowledge, both factual and also linguistic about language. All right, so going back to the observation from before. So we want to understand or analyze the operation of these layers, what exactly they do, what's their role in building the prediction. And we want to try to analyze that in the vocabulary space. So the most naive thing one could do, right, is to take the output from this layer and just project it to the vocabulary, right? This is the most naive thing. And we can do this multiplication and look at the top tokens, right? Which tokens are being promoted by this layer. But unfortunately, this doesn't work. When you do that projection and you look at the top tokens, you will just see a bunch of words not related to each other, not related to the input, not related to the output, basically really not clear. So this is just the wrong resolution to read the output from that layer. And so one of our contribution in that regard was to decompose this output. We tried to increase the resolution at which we look at the outputs from these layers. And so each MLP layer is essentially defined with two parameter matrices in transformers. Okay. So we have two parameter matrices, let's call them K and V. And so for a given input, first we multiply the input with the first matrix. We take a nonlinearity function. It can be ReLU, GELU, whatnot. And this gives us a vector of coefficients that is used to weigh the columns of, the rows of the second matrix. And so what this gives us is that, instead of viewing or analyzing the output from this layer as a single vector, or as a single update to the token representation, now we can view it as a collection of sub-updates, right? Where each sub-update has two components: fixed parameter vector from the MLP layer, right? Each of these, and an input-dependent coefficient, right? So we have a static vector. This is just parameter vector that we got from training, and this coefficient that determines how important this vector is for this particular example. And why is this useful? Because when we start to look at these vectors, individual vectors, instead of the entire output, then we start to see really interesting things. So here's one example. These are the top tokens in the projection of the vector, this vector at this index from layer 11 at GPT-2. And if you look carefully, you will notice that all these tokens are about software engineering, right? So clearly this vector, it's just parameters, right? We took a vector of parameters, projected it. It clearly promotes this concept. It gives high priority to these words, this particular concept when building the prediction. Here are a few more examples. So you can see here examples from two different models, GPT and another model trained on Wikipedia from different layers. And we can see, for example, both semantic concepts like this one, measurement units, and also syntactic concepts like this one, right? And this happens across layers, across models, also other models not analyzed as part of these works. So maybe the takeaway here is that sub-updates in transformer language models, they encode concepts that we humans can often interpret in vocabulary space, right? And these sub-updates build the predictions, right? And so I'm not going to go into details here, but we also showed how that there is correlation between changes in the evolution of the output distribution and the tokens that these sub-updates push when being activated by the input. So just to be a bit more specifically, we analyzed two different events. The event of when the final prediction of the model is being promoted to be the top token in the distribution. And we contrasted that with elimination events where some top token is being eliminated from being at the top. And we saw that essentially the tokens that get to be at at the top of the distribution at the end are those that consistently being promoted by these sub-updates across layers. All right, so just to summarize the main findings, we showed that the MLP outputs can be interpreted as a weighted collection of sub-updates to the token representation or the output distribution. And each sub-update is induced by a parameter vector that we can often interpret what concept it encodes. Yes.
Yeah, you can try to measure like really how much the subspace of this like updates do the projection to the token embedded state, because there could be like a 50% correlation to the words, and then another 50% that is just like capturing other meaning that is not about like the context.
Yeah, so this definitely doesn't work always. So you can see here, in this graph, right? This explains only a portion of the cases. There are many vectors that you project them, you don't see a clear concept, right? This can be explained by actually more than one factor. So for example, there is this phenomenon where the model packs multiple features on the same parameter vector, and then you need somehow to disentangle that.
So how do you measure like when it successfully explains it? Like what's the definition of successfully explained?
Oh, so yeah, in this particular case, we just ran a human evaluation. So we sampled these vectors from different layers, and we let humans look at them and try to identify patterns. And a success in this case is that if the people, like the human who analyzes the projection, can identify like a clear pattern in a big portion of the top tokens in that projection.
Okay, so just the top tokens are kind of like related to each other, and not just like randomly spread.
Yeah.
But I'm saying like they could be related to each other, and still there is like a lot of meaning in that vector that they can see just by projecting the matrix.
Yeah, so yeah, okay, we had more experiments. I will get, actually, this is the next thing, where we actually try to increase like the weights of particular vectors and see the outcome on the generation output. And then you can see that, if you promote a specific concept, if this vector indeed encodes that concept, you should expect this to have influence on the output. Right. Okay. So we will see right now. Okay.
Johnson?
Yep.
Can go back to
Okay,
the
yes, yes.
slide. Just for my curiosity, in the GPT, you don't have this name category. Say
Oh yeah. Yeah, so the thing is that GPT has, this model, like the model we trained on Wikipedia, so we used a much larger vocabulary, and we used a vocabulary that is based on like each token in the vocabulary is a whole word, right? So in GPT, the vocabulary size is much smaller, so names are usually just being broken into subwords, right? So this is the reason. Yes.
Is there any type of what embedding you use? Because there are many types of embeddings. One never knows which one to use. Does it matter, or can you explain something about?
Yeah, so today, I mean, this question was very relevant maybe a few years ago. Right now, when you train a model, like GPT, for example, you train the embeddings together with the model. So you don't really have a particular choice. The choice that you need to make maybe is in terms of the tokenization, like how you what is the vocabulary that you're going to use. This has a lot of effect, but yeah, such experiments are hard to do in the field in general, because then you need to measure how well your model is doing compared to other models, but it's really hard to do it, outside, for example, Google, and so not a lot of people are doing that, and yeah. Yeah.
From your answer to Yair, I understood that this experiment was done by manual inspection, right? By humans.
This one, this one.
I guess you could have inspected only a small portion of the huge number of parameters here. Is there I don't know, maybe you have some other results about metrics, like a more statistical metric or something that you could actually check, verify it across layers, across many parameters, something more systematic?
Yes, actually, I wanted to do that. I tried to do that at some point, but this is super hard task. Like, think about it this way: you have 100,000 of such vectors, and then essentially the task here is semantic relatedness, right? You have two tokens or a set of tokens, and you want to say how much they relate to each other. Right. This is like unsolved task in NLP. So yeah, we don't really have tools to measure that today, but there was a very recent work from OpenAI that actually tried to do that, but they used the model itself. So imagine that they just took GPT-4 and use it to describe the neurons of GPT-2, for example. Yeah, I mean, it will be interesting to try. Actually, I thought about doing that, but then they did it. So yeah. Okay. Great. Any more questions on that? Okay. So, right. So let's move to some practical applications, and also maybe this will address your point too. So the intuition here is that, if sub updates indeed promote concepts and build predictions like that, this has implications in terms of controlling the prediction, because we could increase the weights of concepts that we want to promote, right? And so we wanted to test that in the context of toxic language. This is one of the biggest problems with language models today. They train, on Reddit, for example, and all kinds of websites that include a lot of biases. Essentially, these models are very racist and tend to generate toxic language. And so we want to suppress that behavior. And to do that, we did a very simple experiment. We just searched, in the projections of all the sub-updates in the network, vectors that promote concepts about safety and trust. We just searched like safe, trust, I don't know, thank you, words like that. We found 10 such vectors and we just relatively increased their weight. Just to put this in proportion, like 10 vectors is just 0.1% of all the vectors in the network. So this is like super targeted, very, small change in the operation of the network. So, and we measure toxicity like on a standard benchmark for toxicity. And so if you just take GPT-2 and run it on this benchmark, you have a 60% chance for the model to generate a really toxic language. Perplexity is just like a measure for language modeling quality. And here are the results when using our intervention. And so we basically decreased toxicity chance by almost 50%, and with only a small cost in terms of perplexity. And this is compared to strong baselines that try to do something similar. And here we just like did, very manual intervention in the model, right? So we obtained this very, dramatic change in the model behavior with a very, very, very small and targeted change in its operation.
So when you say increase the rate, and then you just take modify parameters to make this vectors bigger, or you sequence by new?
In inference, I didn't train the model at all. It's just like increase, I found these vectors in a static way without even running the model. And then, each vector like that, it has the dynamic component, its activation. So we just increase it a bit. What it's a bit, just, we check, like we compare, the activations in that layer, and we just like normalize it a bit to be higher compared to other.
Does it make sense to kind of do a fine tuning, like do it in training, in a post-training procedure, like fine tune this in order to, I mean, your solution might hurt perplexity more than it should, right?
Yeah, for sure. We didn't do like it took us 5 minutes to find these vectors.
But is it possible to do like
for sure.
Training procedure?
We didn't try, but yeah, this for sure can be optimized more, for sure. Yeah.
Are you by promoting this small number of concepts, would you be biasing the model in unpredictable ways? Let's say gamers on Reddit use incredibly foul language. Let's say I want to communicate with the model about games. What will happen if you suppress this?
Yeah, so obviously, if you want the model to have a toxic language or to talk like, very.
It will just only represent some type of people, not that language. Maybe you're changing it in way.
Yes, it might be that the model has all these kinds of correlations inside between, I don't know, toxic language and I don't know, specific styles of text, but yes, this might be really like affect other behaviors, but yeah. Okay, other questions? All right, and so actually these ideas can be applied to many different settings, and so we released an open source tool. So if you feel like, I don't know, trying it for yourself, there is an online demo. You can inspect the prediction of any input you feed to the model and also apply interventions and yeah. All right, so from controlling predictions to improving efficiency. And the intuition here is that if we can inspect the evolution of the output distribution, maybe we could identify cases where the prediction is ready, right, earlier in the process. And then we can just stop the computation there and save compute, right? Not running all the layers of the network and just stop earlier. So this is also called early exiting. And so, like we said at the beginning, essentially this operation of converting the token presentation into distribution it gives us an approximation. And so we wanted to improve that a bit. And so instead of projecting, inspecting a particular vector, we first map it into a final layer representation using a linear mapping. So obviously this is much cheaper than running all the layers. And then we inspect that final layer substitute instead of the original vector. And the first observation we had is that, well, in many cases, these models can predict the final prediction way earlier in the prediction process. Or to be more concrete, in 30% of the cases, you actually need just one layer. And, you know, in the larger models, you have, you know, dozens of layers. So this saves a lot of the computation. And actually, we also used it on top of existing state-of-the-art early exiting method. And yeah, using these linear mappings gives us a gain of 8% on top of the already gain from that layer.
Especially if you know which 30% is you can predict at the first layer. Given you see the output first layer, do you know which 30% are correct and which are not?
Yeah, so we don't know that, but there's a lot more to do in that space, I think.
Or I think I don't understand this graph. So you said that very early you gain like almost full precision, but this here we see pretty linear curves.
Yeah, so here we actually measure, like, you know, we have the gold, you know, the true we know what the model predicts at the end, and we just, you know, check if we stop at each layer, how good we are doing. Like here, it's
So
a
wait,
bit.
so can you explain it? So what does this mean?
Okay, so first let's maybe separate the lines, right? So we have the blue lines. This is when we use our linear mappings. The red ones are just when we do direct projection. Okay, so when we do direct projection, like, you know, we don't like the precision at one is just like, you know, when we take the argmax of the projection, how often it matches to the final, you know, prediction that comes out at the last layer, right? So when we do direct projection, you know, at the first layer, it doesn't really work. I mean, in 0% of the cases, we actually predict the final prediction. But when we first take that hidden representation, map it with the linear mapping to the final layer substitute, and then project.
So that's the 30%.
Exactly. But like in general, it's interesting that, you know, in so many cases, you just don't need the rest
But
of the
it's
layers.
interesting that the behavior, so, okay, I understand there is a shift, but the behavior of the curves is pretty similar. That's a bit surprising.
Yeah, it's surprising. Why it's surprising?
Because I would expect that the learning process might be faster, for example.
Across layers, I mean.
Yes.
So yeah, actually, okay, so this is an interesting point. In another work, we show that essentially what happens across the layers is that the prediction is being refined very slowly, in a sense. Like if you look at it in, you know, in a discrete way, like if you look at, you know, given a layer and you look if the MLP layer, for example, change the top one, change the argmax or not, you know, in each layer, it only happens in about 20% of the cases. So it's like a very gradual process. So when you have that in mind, maybe this is not so much surprising, right?
Thanks.
The function is convex and not concave. You think that the last layers are really very important according to this. I mean, it looks like that the last layers are really significant, and not the first 80 layers. The last 20 layers are the most significant.
The methods.
Yeah. So the last two layers are actually special in that in most cases you have very specific biases going on there.
I meant 20 layers. No? Like from
20%.
20%.
Yeah. This is percent because we compare here different models of different sizes. There is something. Okay, so the first layer in the network actually, and the last two, they behave differently than all the layers in the middle. So, yeah.
Why are we measuring like exact match to the model rather than complexity?
Oh yeah, this is just like a like quick demonstration. I mean, that was not the perfect.
Would be enough fact that your benchmark is what the model predicted rather than what the language actually, or like what means so there.
Yeah, you're right. Yeah, this is like okay, our goal in this paper was not necessarily to improve efficiency. So this is just like, yeah, but there are works who like where they do measure perplexity and other metrics more globally. Yeah. Yes.
I have a very naive question. So you said that the last two layers are special.
Yeah.
What, so if you're already intercepting every layer, why wouldn't you apply the special things that you do in the last two layers also to these intermediate layers?
That's a great idea. That's a great idea. We should try it. I mean, yeah, like there are a lot of things to do that in that space, a lot. So yeah, that's a great idea. We can try it.
Good luck.
Thank you.
I mean, I think the main problem is to identify when you can do it and when you can. The fact that when you have more layers, you get more precision, it's clear. But if you want to do early exit, you need to know when to do the early exit. Otherwise, you lose precision.
Yeah, I just think that there are a lot of artificial cues or general behavior or form of the vectors that can indicate that, for example. I think this is what these methods are relying on. Okay, okay, I just realized that there is not enough time for that entire section, but I'm happy to tell you about it. I don't know if you want later. So let's just skip. Actually, that was a very interesting one. Okay, but let's just skip to the end.
Here is interesting.
What? Okay, wow, a lot of slides. I was very optimistic. Okay, so future directions. Okay, I think that this type of research that I just described is actually very new in the field, and so I think we're just starting to scratch the surface, and there's a lot of basic research to do on the internals of these models. So just to list that maybe the most challenges problems in my mind. So first of all, we need better analysis methods for the parameters of the model. Specifically, there's this phenomenon of superposition, where models sort of pack multiple features on the same group of parameters. So being able to separate these features is a big challenge. We also need better inspection methods of representations, like the token representations across layers, to understand, for example, if we can, if the model arrived at the prediction earlier and all of these things we discussed. And yeah, maybe the most interesting one is like understanding how these, they can solve very complex tasks that require reasoning and, all kinds of arithmetic skills and all kinds of reasoning skills. And so understanding how this is done internally, I think it should be very interesting to solve. Beyond that, all these insights, we can use them to generally develop better language models. They can transform, the development cycle we have with language models today at all levels, from, building new architectures that are better than transformers in many ways, for example, to be interpretable by design, also to address key challenges like I demonstrated today, toxicity, the high computation costs, and also, yeah, there are a lot of practical day-to-day practices that are very either arbitrary or inefficient. Yeah. And finally, I believe that the future holds models that do not only process language, they also process vision and sound. And so this also opens a lot of interesting questions for research, like how these models combine information from multiple modalities. Yeah, and beyond, artificial intelligence, we can also apply such insights to natural intelligence or biology and neuroscience. Yeah, and thank you. Yes.
Things are progressing very, very fast, overwhelmingly fast.
Sorry.
I wonder what do you think about your analysis of GPT-2 based on your knowledge? How much of it would apply to current future models?
You mean for natural language processing?
Yes, for
GPT-4, for example, how is the difference? How will be different?
Okay, so first of all, models today, GPT-3, 4, you name it, they rely on the same architecture, the same ideas. So No, but you could also ask, like, if tomorrow someone will come up with a different architecture, not transformers. So I truly believe that, these methods also apply to other architectures. We just like in the work with Leo, Wolf's student, we also had similar ideas for models that like completely different architecture that involves also vision, for example. So
And you use GPT-2 because there you have access to everything.
So actually, in the figures I mentioned GPT-2, but we actually analyze also a lot of other models. Also, I know BERT, for example, Palm, Google's model. They all rely on the same architecture, and so we observe the same. For example, the concepts that I presented earlier, it's in all the models.
And also just the paper from last year.
Oh, a lot of things happened in the 1 year. Yeah. Other questions?
I have a question. So somebody asked this of Sam Altman during his visit here. He gave an unsatisfactory answer.
Okay.
Surprising.
What in when industry is moving so fast and giving so little access to their current models and their current data, what is now the role of academia and what should we do?
So that's a great question, and actually we discussed it over lunch. Yeah, so my take on that is that first of all, the models that are open source, they share a lot of similarities with the closed models. That's in the first place. So they're just a bit smaller. What?
How do we know?
Oh, we know. I mean, no. So yeah, I mean, okay. So at least until ChatGPT and GPT-3, I think also for GPT-4, like, OpenAI said that this is transformer, or, yeah, and also Google uses I mean, people say, like, I don't know, transformer is like if there's new architecture, yeah, maybe we wouldn't know, but yeah, I don't see it coming in the next, I don't know, year or so. I don't know. About the data, yes, that's true. We don't have the data, but there's also, I mean, people don't really know if you actually need all this data, because, after like a few months after GPT-4, I think, came out, so Stanford released their open source models that obtain not that far performance compared to the larger models. So, yeah, it's true that these very large and expensive, models, they are very impressive and all, but, you might not need all that to, all that data and compute to get to something similar. That's what I'm trying to say.
So is there research showing like a graph showing the precision as a function of the size of the data?
So yeah. So that's a great question too. I don't think we have good evaluation today to compare these models. That's another huge problem. There are hundreds of benchmarks, and in many cases, okay, so that's a complex question because, some of these models, let's say ChatGPT, it was actually trained on part of these benchmarks. And so, we can't really evaluate it on these benchmarks because it was trained on them. So yeah, there are a lot of problems in terms of evaluation. I guess that's another huge challenge that also can be solved in academia. I don't know, I think there are a lot of things to do in academia, both in terms of evaluation, works like I do, like understanding how these models work, coming up. I mean, transformers, essentially, they're pretty bad in many cases. I think there are a lot of ways to improve them. And so.
Not to mention the outlaw.
But in a higher layer level, this is not specific to NLP and not specific to machine learning. You could ask the same thing about, you could have asked this about computer architecture for the last 40 years. What's the ability of computer architects in academia versus Intel, ARM, and NVIDIA? It's whenever the innovation impact is a financial gain attached to it, you end up with a situation like we have now in NLP and like we have in architecture and so on, and there are ways to in theory, it's not a big problem.
Some type of a paradox, because if it's not interesting, if it's not interesting financially, it's not interesting. If it is interesting financially, maybe I can do something about it.
That's the reality of computer science.
No, but there you
And here,
in many topics you can improve ingredients, and here there is no ingredient. I mean, it's the whole
but the argument.
it's the whole book, the whole picture.
It's not argument. If you yes, but the flip side of what you have said, if you go to something theoretical that there's no financial implications, then the industry is not facing
There's a talk where he actually compared computer graphics and Pixar and and rendering farms to what's happening now in AI. He did this last week and it's a great talk. And he says, yeah, we've seen this, we've tackled these problems in academia many times over in the past. Basically,
Yes.
What do you think about regulation?
Like government.
AI regulation, I mean, this is the huge question that everybody's doing.
Yeah, I feel like some Bauman, this is how it feels. Yeah,
And we want a more satisfactory answer.
it works for Google. Google wants a moratorium, to get ahead.
עילת הסבירות, we want
no, I think,
תשובה סבירה.
no, I think like, in some sense. Yeah, I think there should be some regulations because. I don't know, I have like personal examples. So for example. As part of, this research about language model internals. So there's also the idea of removing knowledge, right? Where, the model capture all kinds of facts in it. And there's research on how to update or edit this knowledge or completely remove it from the model. So this is one, actually, this is the part that I skipped over. I don't know if we have time, I can go over it. But, so, there is like, yes, there is a GPT, and so there's the Chinese version for that, the Chinese GPT. I don't remember the name, but so one of okay, so one of his developers, so one of the developers of that model, there was recently this conference at Africa, maybe it was CVPR, I don't know, some big conference, and this person came to a colleague of mine and asked him like, he started asking him a question about how we can questions how to apply that method to remove information, very specific information about demographics and stuff, and clearly, such kind of methods can be used to malicious purposes, right? It's not like science fiction, it happens, like, people take these models and use them in very bad ways. And if these models are open to everyone, like ChatGPT, people can do with it whatever they want. They can spread information, like disinformation, they can do a lot of bad things. I know, just take the example from, we try to suppress toxic language, someone else could do the opposite thing. And so, yeah, as long as, these models are open to everyone, I think there should be some regulations.
They're not going to work. It's the same as the social media, gambling, I don't know, all this stuff, pornography, all this stuff. I mean, it's all they cannot control, no control. Yeah, no, because this is a very specific, limited knowledge that is known only for few people, and it's not going on the, on the web. But things which are
on one way, yes. On the other hand, this has a very strong signature, like where you have a farm of computers, and it's something that you can notice. It's electricity. It's so in a sense, it's similar to nuclear farms because you can spot where they are. Okay, so you could control if you wanted to control. You might. I'm not saying. For sure, but at least the big ones.
There is something about comparing AI to.
Here's another perspective.
לעצור את ההתקדמות הגלובלית, שהבעיית הרגולציה העיקרית של העולם זה צ'אט GPT, זה אנשים שהיו סלף-סנטר כשהם אמרו את זה. יצרנו את המפלצת המפחידה בעולם.
לעצור את הסייבר אטאקס.
גלובלית תהרוג אותנו ב-2050.
ואחרי זה נעשה רגולציה.
לימוד בסרט, אנחנו עושים 2050, היה רוב איתנו בעוד 10 שנים. לא יותר דחוף.
הצעת את מילים בלתי ניתן לשליטה.
שאלה מאוד מספרי תמיד לפני 20 שנה כשהתחילו בתולדות נוירונים זה היה בוא נלמד מנורוסיינס. אני חושב במחקר שלך בעיניי מאוד חזר למחקר נורוסיינס בסיסי. זה היה לרופא שמכניס אלקטרון רואה שהיה
למידת תפקידי באופן כללי. בגלל שקשה להבין.
אבל יש...
האם אתם מוכנים רעיונות?
כן, אז האמת שהייתי לפני חודש ב-MIT ושם ממש כאילו יש שילוב ביחד, כאילו בין המחלקות, הם קוראים לזה artificial neuroscience. כאילו מה שאני עושה, הם קוראים לזה artificial neuroscience. כאילו זו הסיבה שהגעתי שם. כאילו, זה תחום יחסית ממש חדש, ולגמרי שני התחומים האלה יכולים כאילו to benefit from each other, לא יודעת, נגיד, משהו שלא הצגתי היום סתם, אז כאילו, יש כל מיני טכניקות, כמו למשל נגיד להתערב בחישוב באמצע, כאילו, למשל כמו בביולוגיה שעושים ג'ין נוקאפ, נכון?
הרעיונות בביולוגיה בדיוק מפלים ב20 שנה.
נכון, לגמרי, כאילו לגמרי. פה פשוט יש לך כלים שבתחום הזה אתה לא יכול לעשות, אני חושבת שזה הבלטלנק העיקרי, כמו למשל שם אין לך אינסוף דאטה, אתה לא יכול להריץ אינסוף ניסויים. לי אתה נותן לי מודל, אני יכולה להריץ כמה ניסויים שאני רוצה, עם כמה דאטה שאני רוצה,
אני חושב שהעניין הוא לא הדאטה, אלא האקסס שלך למה של יש מספיק
אבל הדאטה של... היית רוצה לראות איך נוירון מתנהג, אתה יכול, אבל אתה יכול על אחד, על מעט, היא יכולה להרבה.
גם, אנשים משתמשים...
לא, גם תשווה את העלות של הציוד שצריך בשביל להסתכל על תאים
נראה שזה מרחיב, בסדר.
כן, בדיוק, זה מוח וזה...
יש היום עבודות שהן עושות כאילו בעולם של הניורוסיינסס שהם משתמשים במודלים כאלה בתור כאילו הרצאה של סימולציות לצורך העניין.
תודה רבה.
כל כנס שאני הולך לסוף ב-FCRC, גם בתיאוריה, בסוף זה היה ספר כזה, ההיסטוריה בעתיד, בסוף נגיע לשטט שלי. הדבר היחיד שמדברים על הנושא.
מתי יש? הוא ישלח לאמרי, והוא שם את זה ביוטיוב,
זה מה שהיה עכשיו ב-FCRC.
יש עוד אנשים לא שירצו לראות את זה.
אנשים שואלים מה...
כמה זמן הוא יוכיח משפטים אינטרנטיים.
בדיוק.